Salam and hi. Today we'll learn on Dijkstra algorithm. Okay, what is a Dijkstra algorithm? Okay, a Dijkstra algorithm is another well-known shortest path routing algorithm. Okay, the basic idea behind Dijkstra algorithm is quite different from the Bellman-Ford algorithm or other distant vector approach. It works on notation of a candidate neighboring node set as well as the source own computation to identify the shortest path to a destination. Okay. Another interesting property about Dijkstra algorithm is that it computes shortest paths to all destinations from source instead of just a specific pair of sources and destination node at a time. This is very useful, especially in communication network, since a node wants to compute the shortest path to all destination. Okay, now this is the procedure when you want to do shortest path algorithm. Rule number 1. Make sure there is no negative edge. Set distance to source vertex as 0 and set all another distance to infinity. Rule number 2. Relax all vertices to the current vertex. Rule number 3. Choose the closest vertex as the net current vertex. Rule number 4. Repeat rule number 2 and rule number 3 until Q or reach the destination. Okay, I will give you the two types of example. Okay, so that we'll understand this is the first form, okay, and then this is the second form. Okay, example number 1, example number 2. Okay, so but we go to example number 2 and then we will go back to example number 1 because example number 2 easy to understand. Okay, now go back here. Remember this rule. Okay, now let's start to see example number 2.
Here's another example of using Dijkstra's algorithm for finding minimum weight paths between vertices on a weighted graph. For this example, I'm going to start at vertex A and find the minimum weight or shortest distance paths to every other vertex. So starting at A and going to A, of course, doesn't require traveling at all. So I'll get a weight of 0 there. And since I'm finished considering A as a destination now, I've got the shortest distance, I'm going to put a box around it, and I don't have to put anything else in this column underneath it. I can get from A to B with a distance of 8, or a weight of 8, and the subscript means that I just came most recently from vertex A to get here. And these subscripts are going to help us track where the paths go as we move along. I can get from A to C with a weight of 2, and from A to D with a weight of 5. Notice that vertices E, F, G, and H aren't immediately connected to vertex A, so right now they're unreachable, and I'll mark them with the infinity symbol to show that. Now I look back at this row that I've just completed, and I find the shortest distance without a box. So the boxed one we're through considering, but 2 is the next shortest. So I'm going to copy that down to the next row, and I'm going to put a box around it because now I don't have to think about C as a destination anymore. I've got the shortest path from A to C. And I'll mark over here that I'm considering vertex C now. And the next question is, can I get from C to B, D, E, F, G, or H with any shorter path than what I've got so far? Well, I can't go directly from C to B, so that 8 underneath the B column is unchanged. I can get to D, however, from C with an additional weight of 2. Well, 2 is the minimum to get to C. If I add 2 more, that makes 4. 4 is better than 5, so I'll mark that down here, and I'll put a C as a subscript, indicating that C was the vertex I came most recently from. I can get from vertex C to E with a weight of 5, so 5 added onto the 2 gives me a weight of 7 in total, again coming from vertex C. I can't get from C to F, or to G, or to H, so those are going to remain unreachable. Now the shortest distance or minimum weight that isn't boxed already is this 4, so I'll keep it as my next shortest path here, and it's from vertex C, put a box around it, and so D is the next vertex to consider. Do I have a shorter path to B from there? Well, I can add a weight of 2 to get from D to B. 2 plus 4 is 6, and that is better than 8. So I'll mark the 6, and it came through vertex D. Can I get to vertex E? Yes, with a weight of 1. 4 plus 1 is 5, and that's an improvement over the 7 that we had. Can I get from D to F? Yes, I can, with a weight of 6. 6 plus 4 is 10, so I put the 10 underneath the F column. Can I get to G from D? Yes, with a length of 3. And 4 plus 3 is 7, so I'll put a 7 under here. Can I get to H from D? No, not directly, so I'll still leave the infinity symbol under the H column. Now the minimum weight that isn't boxed already is this 5, so I'll mark that in the next row with a box around it. My shortest path to vertex E comes through D, and it has weight 5. So E is the next one that we're working with. Can I get from E to B? Not directly, so this 6 will not change. Can I get from E to F? No, so that 10 will stay unchanged as well. I can get from E to G, though. So 5 plus 1 is 6. That's an improvement over the 7 that we had. So I mark a 6 here, and we came from vertex E, so that's the subscript. And I still can't get from E to H, so there's still no path yet that brings us to vertex H. So this row is done. Now there's 2 weights in this path that are the same. So 6 and 6. It doesn't matter which one I pick to move forward with. Let's just use the one under B since that's alphabetical order. So I'll put a box around it, and B is the vertex we're working with. Can I get from B to F? Yes, it's a weight of 13. 13 plus 6 is 19. That's not better than 10. So we'll leave the 10 alone. Can I get from B to G? No, so I'll leave the 6 alone. And I cannot get from B to H either, so I'll leave that infinity symbol there. Now the smallest weight that's not used is this 6. So I'll copy it down and box it. And G is our current working place. Can I get from G to F? Yes, with a weight of 2. 6 plus 2 is 8, and that is better than the 10 that we had. So we'll put the 8 down and mark G as a subscript. Can I get to H from G? Yes, with a weight of 6. 6 plus 6 is 12, so I can finally replace the infinity symbol with a 12. Now 8 is the smallest unboxed weight. So I will copy it down to the next row and put a box around it. Vertex F is now where we're working. Can I get from F to H? Yes, with a weight of 3. 3 plus 8 is 11. That's better than the 12 that we had. Now this row is done, and the only thing that's left to do is to mark the 11F here with a box. And now I have all the shortest paths from A to all the other vertices. If I want to know what the path is, which vertices it went through, I just start at the destination. Let's say I wanted to know about this path of 6 to vertex G. It came most recently from E, so it ended with EG. The vertex E had the shortest path to it from D, So it went DEG. And so prior to D, it came from C. And from there, previous, it came from A. So it went A, C, from C to D, from D to E, from E to G. And so that's the path we had to take to get the length of 6, A, C, D, E, G, and I can go back and trace it on the graph. A, C, D, E, G, length of 2, 4, 5, 6. And we could do the same thing for any one of these minimal weight paths that are now in boxes.
Okay, now we go to example 1 back. I recap back. This is a second way you want to write down. Okay, now I show you for the initial step. Then how many? You got node number 1, number 2, number 3, number 4, number 5, and number 6. Okay. Now initial means from node 1 here. D2, node 2. So what happened? 1, 2, 2, node 2. How about the cost? Cost is 3. Okay, now what happened? The next one from initial to D3 means node 1 to 3. What happened? Cost is 2. You put 2. And then how about here? D4 from initial. D4. So how about the cost? Cost equals to 5. How about D5 and D6 from initial? Cannot, because cannot directly from 1 to 6. Must go through node 3. Similarly like D6, D5. D5, you must go something like you must not direct link. Okay. So I want you to understand this thing first. You make the comparison between this example and this example. And then if you don't understand, you can ask me back. Thank you.